de-sequestering as a source of flavour violation.
Thanks. Yeah, thank you very much, especially to all the organizers. It's a brilliant conference, and it's always nice to be in Cambridge. Where else can you give a seminar in a gatehouse? I want to present how moduli stabilization can lead to the generation of new terms in the low-energy superpotential. While these terms are interesting phenomenologically, they can lead to problems such as flavour violation. And this is based on work together with Joe Conlon, David Marsh, and Markus Berg, who's not here because he's putting final touches on the paper, so you can read it next week. As we heard in the talks on F-theory, it is not necessarily possible to decouple local and global effects if moduli are stabilized by non-perturbative effects. Thus, it's imperative to study moduli stabilization. In particular, type 2b string models are very attractive to do so because there are two very celebrated and popular schemes to stabilize moduli, the so-called KKLT type models and the large volume scenario. In both these settings, non-perturbative effects such as Euclidean 3 branes or Gaugino condensation on the 7 branes generates a potential for moduli. And along the same lines, you can also generate new non-perturbative terms in the superpotential for visible sector fields. And I want to focus in particular on new Yukawa couplings. What are the consequences of terms like this? For example, if the Kähler modulus T acquires an F term during supersymmetry breaking, then terms of this form will give rise to new contributions to soft A terms. And if the flavor structure of the Yukawas is somewhat anarchic, one can end up with flavor violation, and this was called de-sequestering in the literature. So what I will do for you, I will not analyze de-sequestering in a very specific string model. Rather, I will analyze a setup which will contain the typical ingredients that you find in a type 2b string model. So what I will do is I will localize the visible sector on a stack of D3 branes at a supersymmetric singularity. Furthermore, I will focus on non-perturbative effects coming from Gaugino condensation on D7 branes. Now I have two choices where I want to locate this non-perturbative effect, and in KKLT type models this will be on bulk D7 branes, whereas in large volume scenarios the D7 branes typically wrap a small blow-up cycle, and I will analyze these constructions in turn. So what are the questions that I want to answer for you during this presentation? First of all, I want to derive a condition when these new Yukawa couplings can occur in string models. Further, I want to analyze the flavor structure, and I would also want to know whether these new Yukawas are suppressed with respect to the tree-level terms that we have. So the outline of my talk is as follows. To be able to do calculations, I will have to resort to orbifolds, and I will just sketch the most important steps of the calculation before I then analyze the two scenarios pointed out before in turn. The superpotential generated by Gaugino condensation takes the following form up there. It's given by an exponential of the gauge kinetic function on D7 branes. And in string theory, the gauge kinetic function typically will be a function of other fields in the theory, such as moduli and matter fields. And I can expand the gauge kinetic function, engage invariant combinations of the visible matter fields. If I then resubstitute an expansion of this form into the original expression, I can see very easily that Yukawa couplings of the type that I want to get are generated in these kind of settings. So in fact, in short, I can say that Yukawa couplings are generated to the extent that the gauge kinetic function on the 7 brane depends on the visible sector field. And I can calculate this in string perturbation theory. I can calculate the dependence of the gauge coupling on the D7s due to matter by analyzing a gauge threshold correction to the gauge coupling due to scalar fields on the visible D3 branes. So this is the calculation that I have to do. And first we note that it's a double traced operator. that I have to evaluate. And to leading order, the string worldsheet that can give me a result of this form is the cylinder. It's a one-loop amplitude in string theory, but it's the only one-loop amplitude that has two boundaries, and so it will be the only contribution, and it is the leading contribution. That's what I'll have to evaluate. The cylinder will stretch from the stack of D3 branes to the D7 branes, and will have to stretch across the compact space. So we can already see that classical winding strings connecting one stack to the other will be very important to get a non-zero result. Now let me look at one particular ingredient of the correlator that we calculate, since this one will give me a very distinct condition on when superpotential de-sequestering can occur. In particular, the overall cylinder correlation function contains this term of three scalar fields, and in the calculation, this will turn into a correlator over these three bosonic coordinate fields. When analyzing this correlation function, we find it does not get any contributions from the quantum mechanical correlator. It's purely given by the classical solutions for these fields, and these are just given in terms of strings connecting the stacks and winding around the compact directions. So in fact, I can find that there is a strong constraint on the allowed couplings, and in fact, for this talk, I can even state that there will be one-to-one correspondence between the presence of classical solutions for this combination of fields and the generation of these non-perturbative Yukawa couplings. In reality, it's just a necessary condition to have these terms to generate these couplings, but for the examples that I will show in the next couple of slides, it's actually a one-to-one relation. So now let me use this very powerful constraint to analyze the first situation, where I look at the example of non-perturbative effects on bulk D7 branes. If I move to the orbifold, the D3 branes at the singularity just become point-like at the origin in the compact directions. The D7 brane, I choose to wrap the first two tori, and to separate the stacks, I separate them along the third torus. To see whether Yukawa couplings are generated, I now simply have to see whether I can wind strings along these directions. And first I noted on the first two tori, I have Neumann-Dirichlet boundary conditions which prohibit any winding solutions. So in fact, I can only connect the two sectors on the third torus, and I can indeed do so. The solution for these three fields is in fact non-zero. And what I find that I do generate a non-perturbative Yukawa coupling, but a very particular one. It's only the combination C3, C3, C3 in the fields that appears. So don't be fooled by this expression. It doesn't mean that it's just the same field that appears three times. The superscript up here doesn't specify fields uniquely. In fact, there are multiple fields that can be labeled as C3. So indeed, I can find that I get new Yukawa couplings between different fields. I can continue, and if I calculate the full orbifold correlation function, I find the following result. And the important point to take away here is how the result scales. So this is a bulk effect, and we expect it to be somewhat suppressed. But what we find is that it's suppressed as a radius to the negative third power if all the compact directions have a size of r. So while these contributions are suppressed, they're certainly not negligible. Now let me turn to the flavor structure of the new terms that we find. How do they match with our tree-level results? And we find that, well, they do not match with the tree-level flavor structure. To remind you, at tree level, Yukawa couplings can only take the particular form C1, C2, C3, and this is certainly not the form that we find. So what I can conclude is that indeed, superpotential de-sequestering can indeed be a source of flavor violation. Now let me analyze the second setup, where the D7 branes now wrap a small cycle. In this case, the D7 branes become fractional D3 branes. And let me also introduce one other feature of orbifold models, and it's that the torus can also be twisted by an orbifold twist, so we have a non-trivial identification under the orbifold. And this is a sector that typically appears in these constructions. Again, to see whether Yukawa couplings are generated, I see whether I have winding solutions. And for twisted sectors, winding solutions are projected out. There is no classical solution for this correlator, hence no Yukawa couplings can be generated in this case. But these are not all the sectors that appear in the orbifold. There is also another sector where only 2 of the tori are twisted, and 1 is left untwisted. And I arrange my model in such a way that the 2 stacks of branes are separated along the untwisted direction. This scenario is actually the same setup that we saw before in the KKLT type models. And so the results are exactly the same. I can wind along the 3rd torus, and I generate a Yukawa coupling that's exactly of the same type as before. So this is an interesting result. It's obtained in the orbifold, but how can we generalize it? And so we found that we get a non-zero result if the branes are at fixed points, which are separated along an untwisted torus in this overall partially twisted sector. In homology, this partially twisted sector is not uniquely associated with these fixed points, but rather shared by all the fixed points on this torus, or equivalently, the 2 branes are at fixed points, which share a homologous 2-cycle. And when we express our result in this language, we have the hope that it certainly extends beyond just orbifold models. And again, in this case, the orbifold calculation gives the same suppression. And the result is exactly the same as before in the KKLT type models. So let me summarize and see whether I succeeded in answering the questions. What I find is that indeed, moduli stabilization due to non-perturbative effects can generate new Yukawa couplings. They take this very particular form where the index on the field has to be the same, which is certainly not what you get at tree level. Furthermore, we find that these new Yukawa couplings scale as the radius to the -3rd power, but they're not suppressed by the full compact volume. And so for the 2 scenarios, KKLT and LVS-style models, I find the following, that yes, non-perturbative Yukawa couplings can be generated, but remember, for the large volume style setups, I can only get non-perturbative Yukawa couplings if the 2 stacks of branes share a homologous 2-cycle. So this is the result that we obtained for Gugino condensation, but one could certainly extend this analysis and maybe look at non-perturbative effects due to instantons like Euclidean 3 branes, and this would certainly be interesting. Thank you very much.
Any questions? Gabby?
So that you have these 3 subsymmetries related to you that you want a 3-point coupling. So if you were looking for a 4-point coupling, you should take a Z4.
If I want a 4-point coupling, then yeah, for example, these wouldn't work. Then Z4 would, for example, allow 4-point operators, yes. And then Z4 also has partially twisted sectors, so one can hope to generate these terms as well.
Timo?
Does anything change in an obvious way if you have also lower dimensional charges, like on the D3 instanton, say, or the D7 brane with flux? If you have a D5 charge and the D-1 charge, so to speak, on that, does one simply have to redo or the computation, or is it clear that the same comes out?
I can't really see how this would change our result here, so I can't give you a clear answer.
Well, it works within the second phase, so it should work in that phase.
Let's thank you.